Hi. So again, as you can see, we're talking about stress transformations. If you're thinking you're seeing deja vu, the whole I've seen this before, you have, if you've seen the other video on stress transformations for axial, right? We started off with a stress block that had sigma x, sigma y, and tau xy associated with it. Probably some coordinate system where it was convenient to do the math, right? And then we rotate this coordinate system xy through an angle theta, and we wind up with the NT coordinate system parallel and perpendicular to that cut. The video last time gave us the stresses normal to the cut, a normal stress in a direction parallel to the cut, sigma n and sigma t. And I kept saying, we'll get to tau nt in another video. We'll get to tau nt in another video. Well, here it is, right? So what we had last time, and again, this is completely repeated, this was the free body diagram that we started with. These stresses are turned into forces by multiplying by area, and because the same depth exists into the page in all parts of the stress block, it's all the same thickness, so to speak, I can relate the change in area, the little dA, to the length in the triangle, right? The length in the plane of the figure by using some trigonometry, by noting that there's a right angle in the bottom left corner of this, because that's the corner of the stress block, and we always assume those are squares, right? And we have then the hypotenuse is the cut line, the adjacent angle was the vertical, the opposite angle was the horizontal, and therefore we can relate using the cosine and sine of theta, using opposite over hypotenuse and adjacent over hypotenuse for sine and cosine, right? So that's pretty much the setup. Last time we summed forces in the n direction to get sigma n, because that eliminated tau nt. Hopefully you're looking at this and saying, hey, wait, if I sum forces in the t direction, won't that get rid of sigma n? I'll just have an equation for tau nt, and yes, you're right, you will. And that's exactly our next step. So we're going to sum forces in the t direction and set that equal to 0. Well, I'm going to have certainly tau nt times dA. I'm going to have a positive sigma x dA cosine theta times sine theta. The dA cosine theta is for the area. The sine theta is for the direction, because x is close to n, so to speak. Or last time when we did some forces in the n direction, we used the cosine to go from x to n. So we have to use the sine to go from x to t, because they're 90 degrees apart, n and t are, right? So it's just kind of a logic thing. And again, because sigma x dA1 is going left, the t-axis goes up and left. That's going to be a positive, all right? By the same token, sigma y is going to be downward. We're going to have minus, because it's downward, because the t-axis goes generally up and left, and sigma y goes down, right? So minus sigma y times the area, dA sine theta, and the y-axis was rotated into the t-axis, right, through angle theta. So that's why we get a cosine. The left-hand face, well, that vertical force again, that's a vertical force tau xy dA1. I'm going to have, looks like a minus, because that vertical force goes down and the t-axis is generally up and left. So it's minus tau xy times dA cosine theta. It's a vertical force, so it would be cosine theta all over again. And I'm going to have a tau xy dA2 on the bottom going left. Well, that's the direction of the t-axis. So plus tau xy dA2, which was dA sine theta. Since it's a horizontal force, multiply again by sine theta, set that equal to 0. Whew. Deep breath. Now what? Last time we said we never talked about the area of a stress block, because hopefully we never have to use it except as a stepping stone, right? We put it in here with all due hope that we eliminate the dang thing, we could divide it out. Every term on the left-hand side is a dA. And again, I'm pulling out my purple pen, and I'm knocking all this stuff out. Wonderful. Now what I'm going to do is I'm going to put tau nt by itself, and I'm going to bring everything else to the other side. I'm going to leave this. I want you to notice this right now. Sigma x and sigma y both multiply the same thing. They both multiply sine theta, cosine theta. I'm going to leave that as sigma x minus sigma y. Sounds goofy. The reason I'm doing it is if you remember last time when we had the stress transformations to get to the normal stresses, each of them had a term that had a sigma x minus sigma y over 2. I want to leave it as sigma x minus sigma y, maybe over 2, maybe not, depending on how the math works out. Spoiler alert, it's going to wind up being over 2, right? I want to leave it there so it looks familiar for when we start talking about the maximum stress. Okay, I want this to look like the same equation as what we had before, except with some variations, right? So it's going to look, I want to have the same general feel to it, if you will, if equations can have a feel. So tau nt, I don't know what the heck Microsoft just did to me, but thank you very much for that. I really didn't want it. Sometimes Word does get a mind of its own, and I have to apologize for that. Equals, well, I'm going to have, as I said, I had sigma x minus sigma y on the left side, so I must have negative sigma x minus sigma y on the right side, which makes some sense. This plus sigma x here would turn into a minus sigma x. This minus sigma y would turn into a plus, and that's what the negative sign out front does for me. And that multiplies sine theta cosine theta. And I'm going to have plus tau xy times cosine squared theta minus sine squared theta. And again, like when I did the normal stresses, I'm in a position where I could use this, but it doesn't really let me have any intuition, right? What does a cosine squared look like? Right? Okay, besides something that was already a transcendental sinusoidal wave function, and I got to square the thing. It'll probably look more like bumps because it's never gonna, it's never gonna cross 0. But yeah, okay. I can't really think my way around cosine squared like I can an angle. So we're gonna pull out some trig. You may remember last time we said that 2 sine theta times cosine theta was equal to sine of 2 theta. Well, what that means for us is that sine theta cosine theta must be equal to 1/2 of sine 2 theta. And the other thing that we used, well, we used 2 of them, but we're going to combine them in a second. We had that cosine squared theta, again, this is from last time, was equal to 1/2 of 1 plus cosine 2 theta. And by last time, I mean the video where we talked about getting the normal stresses, right? Sine squared theta is equal to 1/2 of 1 minus cosine 2 theta. So what I can say then is if I do cosine squared theta minus sine squared theta, is equal to 1/2 of 1 plus cosine 2 theta minus 1 minus cosine 2 theta. Well, the 1's are going to cancel because I've got 1 minus 1. 1 minus 1, those are going to go away. And the 2 cosine 2 thetas, whether they combine, I'm going to have 1/2 of cosine 2 theta. Wasn't that convenient? And that means I can rewrite tau nt as minus the quantity sigma x minus sigma y over 2 times the sine of 2 theta plus tau xy plus tau xy here cosine of 2 theta. And that is my shear stress along that direction. Again, everything comes down to twice theta. The instinct would be, oh, well, we're just transforming forces through an angle. Stresses are from forces, so why can't I just use the angle theta? The reason is because not only does the force change, but the area changes, right? And therefore, just theta won't do, okay? And by way of summary, just to have them all in one place here, we had sigma n was equal to sigma x plus sigma y over 2 plus quantity sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine 2 theta, excuse me. And sigma t was equal to the same looking thing as sigma n, because we identified that t and n are 90 degrees apart. So if I rotate by theta to get from x to n, I rotate by theta plus 90 degrees to get from x to t. And 2 times 90 degrees is 180. And the signs just flipped on my trig functions. Minus sigma x minus sigma y over 2 cosine 2 theta minus tau xy sine 2 theta. Okay, this is just to summarize them all and have them all sitting in one place. Okay, all three of these guys all sitting in one spot. There we go. All right, shrink myself so we can all see it. Right, and again, remember when we add together those normal stresses, sigma n plus sigma t, I think it looks very explicit now. When I add those together, I'm just going to get back sigma x plus sigma y. Okay, so that's stress transformations. That's how we go from a general stress block with sigma x, sigma y, tau xy on it, and we rotate through an angle. Right, positive is counterclockwise. Remember, rotate through that angle, and we come up with new stresses: sigma n, sigma t, tau nt, which we could then, okay, we could draw that out on a stress block. Believe it or not, what we could do, what we've been doing here the last couple videos, is we've been starting off with something that looks like this, x and y, and I'll draw it all positive, but if I had a compressive axial stress, for example, well, all I'd have to do is put a negative sign in there. It works just fine, right? I'm drawing a positive shear stress because I've got a positive force on the positive face. All we've done is we've taken this and we've said, hey, what happens if I instead have a stress block that's rotated like this, that there's some angle theta in here, where now I have my n and t axes. I'm going to have some new sigma t, some new sigma n. All right, this is what we've been doing. This is how we've been going through this. This is where we've been going. This is what the sigma n, sigma t, tau nt equations are telling us, is if I start off with what I have on the left and I want something that looks like what's on the right, this is what I would put on my new stress block. Okay, where this is going in the near future, we can use this and figure out when I get the biggest sigma n, the biggest sigma t, the biggest tau nt. Well, really, biggest sigma n, biggest sigma t, just going to be like the same rotation by 90 degrees apart, as you can imagine. But the biggest and the smallest axial stresses, those are the important ones, as well as the largest shear stress. Thanks a lot for watching.